good morning, or good evening, depending on what time it is when you watch this video. Since a young age, kids are used to playing with puzzles. It serves as an exercise for the brain and entertainment as well. But as we grow, we realize that puzzles are not just a game, they solve real problems and help navigate day to day activities. From going to the supermarket, to the water that goes through pipe systems to reach our faucets, to the robotic vacuum cleaner that navigates our houses, old and new. All of these have a common theme, which is graph traversing. Our project discussed the BFS search algorithm, which is a widely known graph traversal algorithm. It works by visiting the nodes on a level one after another. When the level is complete, it proceeds to the next level. The sequential execution time in this algorithm might be long. That is why in this video we will talk about parallelizing this algorithm on a pathfinder maze-solving C++ code.
So how do we make maze solving faster? This project enhances the BFS wavefront pathfinding algorithm using OpenMP parallelization. By distributing the work across multiple threads, the goal is to reduce execution time on large maze grids and improve CPU memory utilization. It also examines how parallelization affects synchronization overhead, load balancing, and scalability compared to the sequential BFS. Why choose this code? It uses a wavefront BFS to solve a 2D maze, and as the maze grows, the cost grows with it. BFS naturally supports parallelism, since many frontier nodes can be processed independently. It is widely used in AI navigation and autonomous systems, making it a strong candidate for OpenMP optimization.
Hello everyone, my name is Riham Eliami. This slide presents the problem statement of our project. Sequential execution works well for simple programs, but it becomes inefficient for complex maze-solving problems. Therefore, our project applies parallelization to the BFS algorithm, which is the breadth-first search algorithm, to reduce the computation time and improve performance on multi-CPU cores. This slide summarizes the peer review feedback on our project. The reviewers suggested addressing potential limitations, clarifying result validation, and improving the readability. So these points were reviewed and implemented.
Assalamu alaikum. My name is Lulwa Sultan, and I'll be talking about the method that we used in our project, which is the breadth first search algorithm, or BFS, to find the shortest path in a maze. BFS explores nodes level by level using a first in first out queue, ensuring the shortest path. It works on trees and graphs. In trees, it starts at the roots and explores children, and in graphs, it explores neighbors while avoiding cycles by marking visited nodes. We applied BFS to a 2D maze where each cell is treated as a node and adjacent cells are checked until the goal is found. The program takes maze dimensions from the user and then computes the shortest path from start to end using BFS.
Assalamu alaikum. I'm Brenda Alaifi, and I'll be presenting the benchmarking part of our project. The first thing we noticed with our code preparation was that the code we chose was completely randomized, which made it impossible to compare the execution time between different devices due to different random values across different code runs. So we solved this problem by identifying the function that was responsible for randomizing the obstacles placement within the grids, and then we used the modified version of our code to sequential code benchmarking of our project. So after the code preparation, we ran the code across 3 different devices with different CPU specifications using different maze sizes to compare the execution time across those devices and how the execution time varies among different parts of the code and how it grows as the maze size grows. In the next step, we parallelize the code to speed up its performance. But after parallelizing the code, we noticed that some parts of the code suffer from race conditions. So we worked on finding the best methods to resolve the race conditions, and we compared the most 3 effective ways to find the best one suiting each part of the code that suffer from race conditions.
Hello, my name is Zahra and I'm going to explain the race conditions that we run into after parallelizing our code. So we run into two race conditions, the first one being the shared flag race. Looking at the variable impossible, this variable is our finish line and the goal of our parallel function is to flag it with -1 if an update occurs. However, because it's a shared variable being accessed by every thread at the same time, and there is no lock, so it introduces a race condition. So imagine thread A sets it to -1, and milliseconds later, thread B also sets it to -1. The final value might look correct, but what if a third part of the program reads the flag while the thread are still writing? The state is non-deterministic. The lack of synchronization means the threads are fighting over the right, leading to a potentially incorrect final answer. Moving on to our second race condition. This is the more serious race condition, the data integrity race. Here, multiple threads are trying to update the same cell at the same time in our main array. This is a classic wave function like finding the shortest path. If thread A finds a path to the cell with distance 5, when thread B finds a path with distance 8, they will both race to write their values. Because there is no critical section here or lock around the array, the last thread to write its value wins, regardless of whether it's the correct or shortest distance. This immediately breaks our data integrity. We lose control over our correct state of the array, leading to a flawed algorithm results. So we must use a critical section here to ensure only one thread can modify the cell's distance at any given moment.
I'm Ghada Atabi, and now we are moving to our performance analysis where we measured execution time across different devices and grid sizes. We benchmarked the code to identify bottleneck for parallelization, compare performance across different hardware, understand scalability as grid sizes increases. We measured 6 key phases in the program, which are the grid allocation, the obstacle population, the BFS wave generation, and the path setup and tracing, the file input and output. So we did this to find the bottlenecks, and we found them. The obstacle placement in PFC search took over 99% of the time. So that's exactly where we will focus our parallelization effort. The key findings of this table are that laptop A is incredibly fast. It finishes in under 1 second for all the grid sizes, while laptop B and C were on the slower side. They took minutes, especially on large grids. Most time is spent in just 2 phases, which are placing obstacles in the maze and running the PFC search. So thank you for listening. So this is table to conclude it all. After parallelization, we have learned that parallelization accelerates independent tasks, obstacle to a great extent, and that non-current engineering can slow down Interact tasks, which is are the PFC, and it wouldn't be sufficient to add threads, but to add smart locking, which is what would make it run in a truly fast manner.
Assalamu alaikum, my name is Sarah Mahmoud and I'll be talking about the key findings within the literature reviews that we read. So basically we noticed that different studies use different methods in improving the performance of the BFS algorithm. We also noticed that many studies faced challenges such as race conditions. This is where a thread tries to update the same knot, as well as load imbalance where some threads work more than others. We also found that there are communication overheads within some studies and scalability limitations where adding more threads might not actually improve the performance within the code. Thank you for listening to our presentation.